Welcome back again, students. In this video segment, we will consider double integrals and polar coordinates, section 15.3. In order to be able to succeed in this section, it might be a good idea for you to review graphing in polar coordinates if it's been a while. The last time you probably graphed in polar coordinates was in Calculus 2 in sections 10.3 and 10.4. And it so happens that I've uploaded a video for my Calculus 2 class covering sections 10.3 and 10.4. So I welcome you, if you would like, and if you need, to review polar coordinates, graphing in polar coordinates. See my video on Math 190 lectures on sections 10.3 and 10.4. Okay, so let's start this section. Let's bring us up to speed though. I don't want to start digging into double integrals and polar coordinates without maybe taking a short look at where we've been with double integrals. So we started out with a definition of the double integral, and it was a very complicated definition. It involved the Riemann sum, double Riemann sums, and what we did in sections 15.1 and 15.2 is we replaced having to look at the double integral in terms of Riemann sums with looking at specific double integrals over rectangular regions and then converting the double integral to an iterated integral. And then we looked at more general regions, type Roman numeral 1 and type Roman numeral 2 regions. So to back up a little bit, we first considered double integrals over a rectangle, the rectangle, say, AB cross CD. And it turns out that in order to set up the limits of integration for a double integral, we really only needed to look at the integral, or the region rather, in two space over which we were integrating. So all we had to really do was consider looking at the rectangle as our kind of first example, AB cross CD. So let me see if I can get us a nice rectangle, AB cross CD. Okay. So here's our rectangle, AB on the x-axis, CD on the y-axis. And my suggestion to you toward the end of that lecture was that to set up limits of integration, specifically if you want to integrate first with respect to y and then with respect to x, is you consider drawing a green line vertically through your region if your desire was to set up and integrate the integration first with respect to y. So we integrate f of x, y, dy. As the green line passes through the region, it hits C first, and then D when it exits from below to above, and then we integrate that result from A to B with respect to x. And that was one way of looking at the double integral over the region, or the rectangle R, of f of x, y, dA. So if we wanted to integrate first with respect to x, we would maybe consider another line through the region, but in the x direction, and we would put the function into the integral. We would integrate the function first with respect to x, and the red line first enters the rectangle at x equals a and exits at x equals b. Then we integrate that result from c to d. Of course, for this particular case of integrating over a rectangle, you really didn't have to do the line drawing of the lines through the region thing. But this idea of putting these lines through the region sets us up for success in more complicated regions. Specifically, our next region was a type Roman numeral 1 region. Type Roman numeral 1 region looked like a set of points xy such that x X was still between A and B. X still lied between A and B, but the Y values were now not between two constants, but between two functions of X. So the Y values varied between G1 of X and G2 of X. And what that region looked like, just so we get a kind of a picture of it, what it looked like is we were still integrating for X, we were still integrating X between A and B, but we had a more general case here where we had on top not the constant D, but some graph, some function G2 of X, and on the bottom we had some G1 of X. And this is where the drawing of the line through the region, and hopefully you discovered that this is a good idea when you looked at homework and stuff, or as you go through homework. But if you consider just simply draw a vertical line through the region, that vertical line enters the region at the lower function G1, exits the region at the upper function G2. We're integrating the function f of xy with respect to y in that direction, if you will, of the green line, and then we integrate with respect to x as x varies between a and b. Let me see if I can clean up that upper limit a little bit. dx. And let's see if I can clean up my drawing a little bit too here. This is x equals b. Okay. And that gives us our double integral over the type 1 region of the function f of xy dA. Okay, and the last thing we did was we put those functions on the left and right now. We changed our region to a type D Roman numeral 2 region, which was a set of xy values, where the x values, there's my dog playing with his ball, or the x, there he is again, where the x values varied between two functions, h1 of x of y and h2 of y. I think he thinks it's Christmas. And the y values varied between two constants, c and d. Okay, so now a quick graph of that region. Here's our xy axes. The y values varied between c and d, but the x values were functions. They were curves. They were curves rather than straight lines. Okay, where the first curve is x equals h1 of y, and the second curve is h2 of y. If you do the line through the region thing, then as we integrate in the x direction, as we integrate the function f of xy in the x direction, that is dx, the red line first hits the region at h1 of y and leaves the region at h2 of y. Then we integrate that result with respect to y as y ranges between c and d, and that gives us the value of our double integral over the type 2 Roman numeral 2 region, f of xy dA. Okay, and that's our quick review of what we've done so far. Now we need to make a big change in what our region in the xy plane looks like. Our region in the xy plane for this section is going to be given in polar coordinates. So the first type of polar region I want to look at is sort of, if you look on your screen, it is sort of like the rectangle R, except what we're going to be doing is looking at what's called a polar rectangle. Let me write out what that is in terms of a definition. Oops. I'm use symbols that are known to man here, are polar. So in the polar plane, we don't consider x's and y's, we consider a directed distance from the origin, r, and an angle of elevation, theta. Okay, so our polar region is going to be the set of all r thetas, where r varies between two constants a and b. So remember, r equals a in polar form is an equation of a circle of radius a centered at the origin. R equals a is an equation of a circle centered at the origin, radius a. R equals b, center of circle centered at the origin, radius b. And theta, the polar angle theta, varies between two constants, alpha and beta. Let's get an idea of what that shape looks like. So keep in mind, we're in the polar plane now. We're in the polar plane. R varies between a and b, and theta varies between two constants, alpha and beta. So here's, in the first quadrant, a quarter of a circle of radius r. See if I can do this. Here's in in the first quadrant, a quarter of a circle of radius b. Okay, and let's have theta vary between alpha. So there's theta equals alpha, and here's theta equals beta. Theta equals beta. So our polar rectangle, if you will, is this. I'm going to attempt to somehow shade this in. Is this region in here? It sort of looks like a sort of contorted rectangle, and this we'll call a polar rectangle. Okay, so this we'll call r polar, and the idea is to, and we can reduce this to a geometric example. Our idea is basically to consider the volume of a region where the base of the region is this polar rectangle. So let's consider drawing this sort of what it might look like in 3D. So in 3D, so just what we've looked at so far, this r polar, that's the base of our region. Okay, this is in the polar plane, or the xy plane, if you will, placed on top of the polar plane. So now let's take a look at what we're talking about in 3D. In 3D, we need another axis. So we're gonna take a look at our usual place in 3D, the first octant, which is most drawable for me. And let's put this polar rectangle in 3 space. So here is r equals a. Oops, that's not r equals a. Here is r equals a. Here is r equals b. Here is theta equals beta. Here's theta equals alpha. Remember the angles, alpha and beta, or angles, I think I mentioned it, angles of elevation. So alpha just above here is this angle off the positive x-axis, and beta is the second angle there, okay, off the positive x-axis. Okay, so back to our 3D drawing. So above this polar rectangle that we've got drawn in the first octant, we have a surface. We're always integrating z as a function of x and y. Whether we're in polar or rectangular, we're considering the double integral of f of xy dA. So let's see what this might look like, what this 3D region might look like that we're finding the volume of. Let me see if I can do this a little better. So here's going straight up to our region, going straight up to our surface, go straight up to our surface. Here's one edge on top. Let me clean that edge up a little bit. Here's one edge on top. Here's another edge on top. And here's our surface. Z equals some function of x and y. So it's sort of like this polar loaf of bread. If we were to extend it, shrink r equals a down to 0, we'd be looking at like a slice of a portion of a wheel of cheese or something. Okay, so let's consider finding the volume of this creature. In order to find the volume of this creature, all we need is to, well, let's do it this way. All we need is to consider, instead of, remember, when we were considering the rectangular case, in defining the double integral, we filled the loaf of bread with an infinite number of infinitely skinny, if you will, rectangular columns, and then sum those columns up. So we're going to do the same thing, but they're going to be sort of like polar columns instead of rectangular columns. I think this might make sense in a bit. So I'm going to draw a typical, let's call it a polar column in our region. So there's theta equals some value, and then theta equals a small change in that value with the two dotted green lines drawn from the origin. And here is a particular r value at a portion of a circle of particular r value, let's just say r. And then let's increase r by a small amount, let's say dr. Okay, so this change in angle between these two sort of polar lines is d theta, small change in theta. And from geometry, we know that the length of an arc of a circle of radius r and theta and theta value angle theta value d theta is r times d theta. Okay, basically what I'm using from geometry is, if you have a circle, the area of a circular sector of central angle theta and radius r, s equals r theta. Okay. Okay, so the area, and this is where it gets a little interesting. The area of this little tiny polar rectangle that I have, and there's not a real rectangle, it's approximately rectangular, but the edges are, first of all, the two opposite edges in the r direction are not parallel, and the other edges are little pieces of a circle, but they're little pieces of a circle. They're so small that they're approximately linear. And the theta, d theta, is also so small that the polar little line segments are approximately parallel. So this is approximately a little rectangle, and the area of a rectangle is length times width. So the area of the base, we'll call that, let's say, dA, is r d theta. That's the length of the little tiny polar rectangle times dr. And you might think, well, there's error involved here. This isn't exactly a rectangle. Well, the error is infinitely small, since dr and d theta are infinitely small. That's the physics argument, and it holds water. This argument is just fine. So this is r dr d theta. Okay, so that's the area of the base of this polar column. Now let's draw the height of this polar column. I'm going to draw in a different color. I'll take a chance here that it won't mess things up. Here's the polar column going up into our region. Polar column going up into our region. So we see a little, or a skinny little polar box going up to the into the region. The volume of that little polar box is the area of the base times the height. The height is the value of the function at x and y. The area of the base is r dr d theta. Now there's one little change that needs to be made here, though, because you notice in the expression that I have the rectangular coordinates x and y. Well, if x and y correspond to, say, the corner that I've got heavily dotted off, then f of xy is the height, okay, because remember our surface is z equals f of xy, but polar coordinates are x given by x equals r cosine theta and y equals r sine theta. So this is we can't really ever escape from the idea that we have a connection between x and y and r and theta. So the volume of our little polar box we'll call dv is then f of r cosine theta, r sine theta, r dr d theta. Okay, the bottom line of all this is that we're looking at the double integral over our polar rectangle of f of x, y, dA. This is what we're starting with. And since the base of our region is polar, then we can replace the f of xy dA, if you will, with f of r cosine theta. So we're going to substitute into the integral x equals r cosine theta, y equals r sine theta. The dA becomes, the dA before, when we were integrating in rectangular form, could be considered as dx times dy or dy times dx. But our dA now, our dA becomes r dr d theta. One of the first mistakes that's made by students is to neglect the r in this. We must have r, and we don't just go from dx dy to dr d theta. Dx and dy you can view as r dr d theta. So don't forget that little extra factor of r. Now the limits of integration, this is not a double integral. We're evaluating a double integral, but we've replaced the double integral with an iterated integral as r varies between the constants a and b, and theta varies between the constants alpha and beta. Okay, so this is our first formula, if you will. It's for the evaluation of a double integral over a polar rectangular. Let's stop with the theory and do an actual example. So example: find the volume of a sphere. Using calculus, of course. Find the volume enclosed by a sphere. So let's do that. Let's find the volume enclosed by the sphere x squared plus y squared plus z squared equals 16. Okay. So to find the volume of this sphere, what we're going to do is we're going to find the volume of the upper half of the sphere, because the upper half of a sphere can be viewed as a function of x and y. Z is a function of x and y, and then we'll multiply that result by 2. Okay. So the solid we're considering is a sphere. Let me see if I can actually do this, do a drawing for us. So let's draw the sphere. 3D. And let's give it some perspective here. So we're interested in the volume of this sphere. X squared plus y squared plus z squared is a sphere. It's a sphere of radius 4 centered at the origin. Okay, so I'm going to set up the double integral, which gives that volume. The double integral is, or the volume is the double integral of the z value. And again, remember, I'm considering the volume of the upper half of the sphere, and the upper half of the sphere is given by, if we solve for z equals the square root of 16 minus x squared minus y squared. So the volume is the double integral of the square root of 16 minus x squared minus y squared dA over the region R, and it's a polar region. It's a circle in the xy plane. The region that we're integrating over is a circle, R polar, in the xy plane. So that's the upper half, the volume of the upper half of the sphere. Multiply that by 2 to get the lower half of the sphere as well. So we're going to use our formula, if you will, our formula just above here. And see, I'll highlight it in red if my surface will allow me to. Today it will. Oops, got to keep it highlighted though. Okay. And our formula says that all we need to do is look at the region in the xy plane, or in the polar plane, to get our limits of integration. So in the polar plane, that's can also be considered the rectangular plane xy. On the polar plane, the region in the base of our region, or the area in the base of our region, is a circle. The circle. So here's, in the xy plane now, our region, or the base of our region, if you will. Okay, so this is now an image in the xy plane of the polar region over which we're integrating. So it's a circle. Well, what's the equation of the circle? Well, the sphere has equation x squared plus y squared plus z squared equals 16. And this circle is part of the sphere when z equals 0. And when z equals 0, we get x squared plus y squared equals 16. So this is a circle centered at the origin of radius 4. We need it in polar form, and this is one of the easiest equations to put into polar form. X squared plus y squared in polar form is r squared, so r squared equals 16. If we take the positive square root, r can possibly be negative in polar form. That's one of the nightmares in trig of polar coordinates, but in this case we could just take r equals 4. So we have this is the equation, r equals 4, of that circle, of our r polar. This is r polar. It's the region over which we're integrating. So back up to our integral. The integral then is 2, and the 2 again comes from the idea that we're looking at finding the volume of the upper half of the sphere and then multiplying by 2 to get the entire sphere. Look back at our formula in red. It's the value, we're integrating the value of the function in polar form. That means we replace x and y with r cosine theta and r sine theta. Okay, if I replace in our integral x equals r cosine theta and y equals r sine theta, 16 minus x squared minus y squared becomes 16 minus r squared. Okay, dA, which in terms of physics we call a differential element of area, is r dr d theta. Okay, now this integral is not a double integral, it's an iterated integral. So we need limits of integration. Back to our polar form. Draw a little green line or red line or any line, not vertically through our region, not horizontally through our region, but radially through our region in the polar direction, if you will. R varies along this green line from 0 to, when it hits the circle, 4. And then what kind of theta is it going to take to sweep that green line around the entire region? Theta varies between 0 and 2 pi. And that gives us, that's the iterated integral that gives us the volume of our region. Now that integrated integral is not very difficult, so I'm not going to take video time to evaluate it. You would evaluate first the inner integral with a simple u substitution, u equals 16 minus r squared, and then du is negative 2r dr, etc. Very, very simple Calc 1 integral. If you go through the actual integration, you end up getting, let's put the dot 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 here to indicate that there's some integration work to do. You end up getting 256 pi over 3 cubic units. Now you can either go through the algebra and calculus to evaluate this integral if you're so inclined, or you can wait until homework to do your homework problem. So you'll be doing plenty anyway. But just to compare this result with geometry. So let's compare result with geometry. In geometry, we learn the volume of a sphere is 4/3 pi r cubed. So the radius of our sphere is 4 cubed. 4 cubed is 64, times 4 is 256 pi over 3. This checks out perfectly with what we got by calculus. So if all we needed to do was to find volumes of spheres, we could have cut to the chase much more quickly by using a result from geometry. So this case is obviously the special case, but it's a good introductory case. So here's a little bit of a reason why you might want to consider doing this in polar form as opposed to rectangular form. We could have done this in rectangular form using the method we discussed in 15.2. If you look back at our region, at least the region over which we're integrating, and I'll do this in let's say blue pen here. Our region again was x squared plus y squared equals 16, or y equals plus or minus the square root of 16 minus x squared. So if we view this as a type Roman numeral 1 region, then our volume integral in rectangular coordinates, our volume would take on the appearance, double integral, it's always a double integral of the function, dA over the region d Roman numeral 1. So it would look like the square root of 16 minus x squared minus y squared dy. Remember, Roman numeral 1 integrates first with respect to y. As we enter the circle with a little blue vertical line, we first start with the lower limit of integration, the lower portion of the circle, so square root of 16 minus x squared. Then the little blue line exits the circle at positive square root of 16 minus x squared. Then we integrate with respect to x, as x varies between, well, it's a circle of radius 4, so x varies between negative 4 and positive 4. We multiply by 2 to get the lower half of the sphere. This integral is not so simple to evaluate. as the integral in polar form. In polar form, a simple U substitution works. In rectangular form, not so much. In rectangular form, to integrate the square root of 16 minus x squared, held fixed with respect to y, and then minus y squared, we'd have to make a trig substitution, and it's messy. So in rectangular coordinates are not always the way to go. And we're going to find that in some sections upcoming that sometimes even polar coordinates are not the way to go. We need another kind of set of coordinates for 3D. We'll cross that bridge when we get to it. Okay, for now, we're looking at double integrals in polar form. Okay, so let's take a look at another example. In fact, the examples, with the exception of our very last example, our examples are to find different portions of volumes of different portions of the same sphere, x squared plus y squared plus z squared equals 16, but captured within different regions within the sphere. So in this case, we have the volume of the entire sphere. So our next example is to find the volume enclosed by the sphere again. Find the volume enclosed by the sphere. Find the volume enclosed by the sphere x squared plus y squared plus z squared equals 16, but within x squared plus y squared equals 1. Okay, what does this mean? We're still in the sphere. We're still in the sphere, centered at the origin, radius 4. But we're finding the volume enclosed by that sphere, but within x squared plus y squared equals 1. Remember that x squared plus y squared equals 1, that's an equation of a cylinder. The z value is missing, so it's a cylinder that extends in the z direction of radius 1. Okay, so imagine a sphere of radius 4 and then taking a cylinder of radius 1 and passing it through the sphere in the z direction, through the sphere and through the center of the sphere. I want the volume that results of this sort of hole that I'm boring into the sphere. Okay, so to do this, let's get a 3D picture of this if possible. Let's see, we'll try it. So here is the portion of our sphere. Let's put this sphere in 3D. First, we'll put it in 3D by drawing the y and z axes. Then we'll come back and draw the x-axis through here. I don't need to get too fancy, but I might as well try to use this for the first time. This is the ruler feature. If it doesn't work, I won't use it. So oops, it sort of worked. Bear with me, this is like the second time I've used the ruler in this business here. So here's the x-axis. Not so bad, I got a little extra bit in the x-axis, but that's all right. So here's our sphere. Here's to give it a little dimension. A little too much coffee today going on. Here's our sphere, and through this sphere, I'm going to be passing a cylinder. Okay, so I might as well try this again with the ruler. And that's about 90 degrees. The ruler doesn't let me lie though, so okay. Let's see. Oops, 86 degrees is really off. And 89 is all right. Okay. I'll be happy with 89 degrees. Get rid of that. And here is, so this is not to scale at all. Here is our volume. Let's going to take a little more practice for me. Let's draw a portion of that cylinder in the XY plane. That's really the most important part of our drawing. Okay. Might have been better if I did it freehand. Okay. So, hopefully you're able to see with me a cylinder, and it looks like a little bit a radius greater than 1, but a cylinder of radius 1 passing vertically through the sphere. The volume that I'm looking for is just the volume of that inner column that's bored out, but it's not the volume of a cylinder. The top and bottom of this little portion here are the caps of this volume, if you will, or portions of the sphere. So this isn't going to be the volume. I'm not looking at the volume of a cylinder. Okay, so what I'm going to do is I'm going to find the volume that lies above the XY plane, and then I'll multiply it by 2, just like I did in the previous example. So above is still, the surface above is still z equals the square root of 16 minus x squared minus y squared. Is still the cylinder. Below, the same thing. Again, we're going to look at above the XY plane first. So the volume then is the double integral over the, let's say I'm going to put r in the XY plane for the base of our region, over the region R. It's not a rectangle. I'm still using R. That's all right. Of the square root of 16 minus x squared minus y squared dA, multiply by 2 to get the lower portion of the volume. And I'm going to go right to polar. In order to go to polar, all I need is the projection of our region into the XY plane, and that's just that little circle of radius 1. That R is the circle of radius 1 in the XY plane. So replace this double integral with an iterated integral. The iterated integral takes place over a circle of radius 1 centered in the XY plane. So here is R placed in the XY plane. R varies between 0 and 1. Little green line. R varies from 0 to 1. And then to sweep out this entire radius R, or radius 1 circle R, theta goes from 0 to 2 pi of the square root of 16 minus r squared r dr d theta. dA is always r dr d theta, not dr d theta. Don't forget the little extra r when you integrate when you're integrating a polar integral, or integral in polar form. Again, the integral is very simple. Use substitution. If you decide that you want to do it, you want to evaluate it, then I verified the value a whole mess of years ago. The integral should have the value 2/3 times 64, is a very bizarre number here, minus 15 to the 3/2 times 2 pi, and the units are cubic units. The most important thing, and you've discovered this, I hope, by doing some homework problems on this double integral business, the most important thing and the most difficult thing is setting up the actual integrals that give you your volume and such. Okay. We're going to change up our regions a little bit. We're gonna move from our regions being polar rectangles, that is r varying between constants and theta varying between constants, to sort of the type Roman numeral 1 polar regions. Not quite the best terminology. So if you'd like to take a little break now, that would be great. Or you could just keep watching. I hope you noticed that the evaluation of double integrals depends entirely, for us at least, on what the projection of the solid that we're considering in 3-space is in 2-space, in the xy plane. And to develop the actual techniques for evaluating double integrals, we looked at different regions. We looked at, in the xy plane, our projections were different regions. We looked at first a rectangle, AB cross CD. Then we looked at type 1, Roman numeral 1 region, function on top, function on bottom between two endpoints x equals a and b, type Roman numeral 2 region, function on left, function on right, captured between two y values c and d. And then we just finished up looking at a polar rectangle. We looked at where the projection of our region in the xy plane was our polar rectangle, r polar, and that was the set of all r and theta, where r or alpha, we consider theta, the angle first. Theta varied between alpha and beta. I think I had r varying first in the set, and r varied between two constants a and b. And what that got us was a region that looked like this in the xy plane. R equals, let's do this again here, or some of it again. Here's theta equals alpha. Here's theta equals beta. Between r equals a and r equals b. So r equals a was this distance, and r equals b was the distance to the outer edge, if you will, of our polar rectangles. And this was r polar. R polar. So we're going to switch things up in the same way we switched things up when we went from rectangular to a type D Roman numeral 1 region. So we're going to take the r equals a and r equals b and generalize them from arcs of a circle to arbitrary polar curves. So we're going to make them, if you will, squiggly. So that I'll make that a little more clear in a second. In fact, right now we're going to look at now D-polar, not D sub Roman numeral 1, D sub Roman numeral 2, but D-polar, where we're still looking at points in the polar plane, and we're still considering theta varying between two constants alpha and beta, but r varies from some function, non-constant function of theta, to another non-constant function of theta. And once again, for a review of graphing equations in polar form, you might want to see my Math 190 lecture online on YouTube, covering sections 10.3 and 10.4. We can't escape having to graph curves in polar form. Okay, can't get away from that bad news, and it usually is bad news. So if it's been a while since you've graphed in polar form, you probably have a lot of company. That's just guts to be done. Okay, so here's what our region looks like or generalizes into now. So here's, let's say this is theta equals alpha. Here's theta equals beta. Here's h1 of theta. So r equals h1 of theta, and here's h2 of theta. R equals h2 of theta. So we've taken the constant r values, the arcs of a circle, and changed them to more general forms. Okay, so let's see what this is sort of translating into in 3-space. So here's our polar. And let's see if I'm lucky today. And I'm going to be able to draw this, just interpret this idea in 3 space. We'll see. So here is 3 space. Here is the first octant. Here, back to our polar. I put it into the first quadrant in the polar plane. So here's our polar drawn in 3 space. So here's theta corresponding to theta equals beta. This is corresponding to theta equals alpha. Here is above in our region R polar, we're looking at R equals h1 of theta as our first function. Remember, functions in polar form are measured from the origin radially outward. So we don't go up and down or right and left, we go radially outward. So here's R equals h2 of theta. Let me clean h2 of theta up a little bit. Here is h2 of theta. There we go. So in the actual polar, in actual 3 space, here is h1 of theta. And see how I'm going to do this. Here's h2 of theta. So our surface is still z as a function of x and y before we insert the polar coordinates r cosine theta and r sine theta for x and y. And here's our surface above. So I'm going to go up to our surface, up to our surface, up to our surface, maybe make it more up-ish. Up to our surface, up to our surface. I'm going to try to draw our surface now. Above, we have z equals some function. So here's sort of the top of our surface, our solid. So there's a representation of our solid in 3D. I'm trying to clean it up a little bit. I should probably just stop. Okay. The only thing that really changes here are the innermost limits of integration. If you draw that little green line that I keep referring to, or red line for the type Roman numeral 2 region, through our region, our general polar region, that little green line determines our innermost limits of integration. Put into perspective in 3 space, here's the little green line. That little green line enters at h1 and leaves at h2. So the double integral over our polar region, our general polar region of the function of xy dA reduces to a doubly iterated integral. I don't think they refer to it as doubly iterated. They just call it iterated integral of f of r cosine theta, r sine theta. Don't forget the r in r dr d theta, r dr d theta. Green line, r varies from h1 of theta as it enters the region first. As it passes through the region, it hits h2 of theta, and theta varies between the constants alpha and beta. Okay, so while the expression looks pretty complicated, there's not that much of a difference between the polar form for a polar rectangle and for a general polar region. So highlighted in red, I have our formula, if you will, for integrating over general polar regions. Okay, so let's do an example. The example is still, like I said before, with the exception of our very last example, our example still involves the volume of a portion of a sphere. Okay, so example. Find the volume enclosed by the sphere. Find the volume enclosed by the sphere x squared plus y squared plus z squared equals 16. But the volume is going to be enclosed within another cylinder, but not a circular cylinder. In fact, well, it may be a circular cylinder, but there's a little difference going on here. Within the cylinder, R equals 4 sine theta. Okay. The elephant in the room now is that we have to remember how to graph R equals 4 sine theta. I refer you directly to my 10.3, 10.4 video for Math 190. To get to the graphing portions, you might want to let the video load and then just thumb through the. It's a long lesson. Thumb through the video until you see the formation of curves. I think it's a nice little review for you. Okay. In any case, this is our problem. The polar equation R equals 4 sine theta happens to be another circle, but the circle is not centered at the origin. This changes things kind of dramatically for us. R equals 4 sine theta is a circle, although that it's actually a circle is not terribly important here. It is a circle. That circle is now centered along the y-axis, and it looks about like this. It's a circle of radius 2 centered along the y-axis, centered at actually 0, 2. Okay, that's not important to know. What's important to do, though, is to be able to draw it, so or approximately what the closed form should look like. So this is a circle of radius 2. If we look at it in the xy plane, in 3 space, it's a cylinder. It's missing the z coordinate, so it is a cylinder in the z direction. So I want to try my best to draw the region in 3 space that we're finding the volume of. Although we could, in this case, probably get away with just the region D polar without our 3-dimensional drawing, but I think it might be instructive to see this in 3 space. So, okay, here we go. First of all, the sphere in 3 space. So here is the big sphere in 3 space. And here's the portion in the YZ plane. Let me get some axes here. Let me impose some axes. Okay. My drawing's getting a little big here. That's okay. So I need 3 space here. So I'm gonna get the x-axis here. I'll just draw it freehand. Here's the x-axis. Here's the negative x-axis. And let's get some dimension on our sphere. So here's our sphere. This is the sphere. X squared plus y squared plus z squared equals 16, or the sphere we've gone through the entire almost the entire lecture with. X, y, z. Now I'm going to draw this circle dipolar in this drawing. The center of the circle is along the y-axis, and that says that the circle in red is about like this. Okay, so the little red circle I just drew, that's the same dipolar above in 2 space. Now imagine that little red circle is just one cross section of this cylinder that extends infinitely and is in both positive and negative z direction. When it hits the sphere, that intersection should look something like this. Okay. I'm only going to be drawing the portion of our volume above the xy plane. So this also happens below the xy plane. So let me give you a little more perspective here. Hopefully you're seeing what I intend for you to see, and that is a sphere, a circular cylinder, not centered along the z-axis, but a circular cylinder smashing through this sphere and forming a portion of the sphere. Okay. Okay. Let's find the volume. Let's find the volume. The volume, to get both the upper and lower portions, 2 times the double integral over the projection in the xy plane, dipolar, of the square root of 16 minus x squared minus y squared dA. The basic setup is a double integral. Okay, so now let's go to polar. Draw a little green line through our projection in the xy plane. If I drew it in 3 space, if I draw it in 3 space, it will look about like that. So that little green line determines our inner limits of integration. R varies, r d theta, R varies from 0, and then that green line exits at R equals 4 sine theta. So in terms of the formula in above, which turned from red back to black, the h1 of theta is 0. The h2 of theta is that variable limit of integration, 4 sine theta. Now, that little green line segment can also be used for us to determine the limits for theta. Theta, then, in order for that green line to sweep through the entire region in the xy plane dipolar, theta should start at 0, not go all the way around to 2 pi, which I was going to write anyway, but go all the way only to pi. Okay, multiply that by 2 to get the lower portion of our volume, and we get our volume integral. Okay. Again, I'm not going to evaluate this integral. It's a simple, well, relatively simple integral to evaluate. I think we'll have a power of cosine in there. It turns out to be 128 over 3 cubic units. So if you decide that you'd like to go through the mechanics here and the algebra and the calculus to get that integral, it's 128 pi over 3 cubic units. Okay. All right. So most of our work is done in this section. Our last idea is to go back and look at the final application I gave you for double integrals in a previous section. I can't remember if it was 15.1 or 15.2. Remember that if z equals 1, if z equals f of xy equals 1, then the double integral of f of xy dA over whatever the region looks like, which turns out to be the double integral of just 1 dA, turned out to be the area of the region D in the xy plane. That doesn't change here. For integrals in polar form, the area of D polar or D or polar rectangle or whatever is still the double integral of 1 dA over our region, D polar or whatever our region looks like. But dA changes to r dr d theta. So if you simply integrate r dr d theta, we can interpret this double integral then not as volume, but as area. So our last problem is to set up the integral, iterated integral, which gives the area of a particular region in the polar plane, not volume but area. Excuse me. So let's just set up the integral. Integral, which gives the area, let's say outside r equals 1, so circle of radius 1 centered at the origin, and inside a kind of common polar graph, r equals 1 plus cosine theta. And I think in my Calc 2 video that I keep referring to in section 10.3 and 10.4, I graph a similar one. The second curve here turns out to be a heart-shaped curve, known in math circles as a cardioid. Cardio means heart, so this is a heart-shaped curve. So first thing we're going to do, as we do for most area problems, we're going to sketch the region. So here's the xy plane, copy of the xy plane. Let's see, here's a circle of radius 1. Let's do this. Our circle, move it, circle radius 1. And here is what this cardioid looks like. Here is what our cardioid looks like. We do this. And it comes around. And looks about like that. Okay. So I want the area, I want the integral, which gives me the area outside r equals 1, so it lies outside the circle, but inside the cardioid. Okay, so what I'm going to do is I'm going to take my little green line, which helps me set up limits of integration, and I'm going to set up my integral. The area is equal to the integral of 1 r dr d theta, or just the integral of r dr d theta, over our region D. So we're going to convert this to an iterated integral. R dr d theta. Now back to the green line. The green line first extending radially outward, it first hits the circle of radius 1. And then it passes through, for the second time, passes through our region when it hits the cardioid. 1 plus cosine of theta. For this problem, the values of theta are very, very easy to see. If you imagine that little green line sweeping through our region D, the lower value of theta should be minus pi over 2, the edge of quadrant 4 along the negative y-axis, and then to positive pi over 2. In general, to determine where the two curves intersect, you would set the two curves equal to each other and use some trig to solve the equation for theta. The idea here was just to show you an elementary problem that uses double integrals to evaluate area, and then you would evaluate this integral. The integral is very simple. A lot of these integrals result in powers of sines and cosines, which aren't too tough. And that takes us to the end of our section. If you decide that you want to actually go through and evaluate this integral, aim for getting 2 plus pi over 4 square units, or you can wait for homework problems. In any case, like I said, this ends our section, and I'm looking forward to talking with you again soon.